At graphing the cosecant and secant curves here in section 4. Notice for the cosecant curve, first of all, I hope we remember that's the inverse, or not inverse, the reciprocal of sine. So you can see I have the sine curve pictured here. Sine curve has our critical points at 0, pi over 2, pi, 3 pi over 2, and 2 pi. We should be well aware of those. And we're simply going to use that graph or that curve to actually graph the cosecant curve. So we would plot the regular points that we have for sine, starting here at 0, maximum at pi over 2, cross the x-axis at pi, lowest point at 3 pi over 2, and back at our original place there on the x-axis at 2 pi. Everywhere the sine curve crosses the x-axis, we have what's called an asymptote line. You should be familiar with those with our work with tangent and cotangent. Asymptote lines are simply going to mean that cosecant is undefined at those asymptote lines. So our sine curve crosses the x-axis at 0, crosses it here at pi, and crosses here at 2 pi. So each of those three spots, we have a set of asymptote lines. And then we use the maximum point here at pi over 2 as a vertice for a parabola that opens up, and that parabola then represents the graph of the cosecant curve. Now, just like we talked about with tangent and cotangent, our graph gets closer and closer to the asymptote lines but never crosses or touches. And if we come down here to our minimum at 3 pi over 2 and -1, we have a parabola that will open down along those asymptote lines. And again, I'm getting closer and closer to those lines but never crossing or never touching. So the actual blue part in this graph is the graph for the cosecant curve. We just use the sine curve to get there. Notice we have the same critical points, 0, pi over 2, pi, 3 pi over 2, and 2 pi, which means we have the same period length, 2 pi divided by b. We have the same amplitude. This one goes up to 1 and down to -1, or our a value. Any phase shift, any vertical translation would apply the same way it applies to sine. So sine and cosecant reciprocal functions will essentially use the sine curve to make the cosecant curve. And the same rule would apply for our secant curve. We'll use the cosine curve to get that. So notice we have our cosine curve graphed here. Cosine and secant are reciprocal functions. Our critical points at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Hopefully by now we're pretty well versed on what the shape of the cosine curve looks like. But just like we have with the cosecant curve, anywhere this graph crosses the x-axis, first one occurs here at pi over 2, second one occurs here at 3 pi over 2, we'll have those asymptote lines. Again, that means that secant is undefined at those points, so at pi over 2 and 3 pi over 2 there is no secant values. And then I'll start here with our lowest point because that gives us a full parabola here. Our minimum here is a parabola that opens down, again approaching those asymptote lines but never crossing or touching. Notice we have two maximum points. Since we're starting our curve here at 0, we'll just graph part of that parabola on this side, and we're ending it here at 2 pi, another maximum. So we'll just grab the other part of that parabola on this side. So essentially we have two full parabolas, one that opens up, one that opens down for both secant and cosecant. The secant has that cut in half with one on each side using those maximum points, and again plotting from 0 to 2 pi. Same critical points. I'll highlight the pi over 2, the pi, the 3 pi over 2. So we've already established the period length is the same, the amplitude is the same. We go up to 1 and down to -1. Our graph just starts at 1 and goes up. Our start graph starts at -1 and goes down. So there's a quick look at the sketch of a secant and a cosecant curve. Now we'll go ahead and make one of those from scratch. Our first one says to sketch a period of y equals 2 cosecant of 2x minus pi over 6. Then we'll graph a period before and after the original. So if we're graphing cosecant, we're essentially going to start out by graphing sine. And to graph sine by hand, we're going to take and find our first three critical points. So we'll take the 2x minus pi over 6, find a starting point by second equal to 0. 2x minus pi over 6, we'll find a quarter point by second equal to pi over 2. And 2x minus pi over 6, find a midpoint by second equal to pi. I'll add pi over 6 to both sides here to solve. So 2x equals pi over 6. Divide by 2 is the same thing as multiplying by a half, and x equals pi over 12. There's our starting point for our new graph. I'm going to repeat the process here. Subtract pi over 6 from both sides. Actually add pi over 6 to both sides, my bad. To add, I need common denominators, so I'll rewrite pi over 2 to be 3 pi over 6. 2x now equals 4 pi over 6. 4 pi over 6 simplifies to be 2 pi over 3. I want to solve for x, so I'll divide by 2, which is multiplying by a half. 2's will cancel, and our quarter point is at pi over 3. Just zipping through the math here, I'm going to add pi over 6 one more time to find my midpoint. Pi plus pi over 6 is 7 pi over 6. Divide by 2, multiply by a half. X equals 7 pi over 12 is our midpoint. And as we have discussed with our other graphs that we've looked at so far, sine, cosine, tangent, and cotangent, our critical points all should be the same distance apart. That distance is easier to see if we write those all with a same denominator. So 12, 3, and 12 have a common denominator of 12. So I'll leave the first one as it is. I'll change pi over 3 to be 4 pi over 12. And I'll leave 7 pi over 12 as it is. From there it should be pretty easy. From 1 to 4 to 4 to 7, we're adding 3 to our numerator. So my next critical point is at 10 pi over 12 and another one at 13 pi over 12. So we'll start there with our one period. I'm going to put those points on my x and y axis. I'll probably go down right down the middle here. Let's try that again, see if we can go a little bit straighter. And we'll go all the way across here. Oh, I have pi over 12, 4 pi over 12, which I'll simplify to be pi over 3, 7 pi over 12, 10 pi over 12, which I'll simplify to be 5 pi over 6, and 13 pi over 12 for my first period. Now I'm going to scroll back up here just to take a quick peek at a couple things. Number one, I'm graphing the sine curve, and number two, my amplitude is 2. So I'm going to mark that on my graph going up to 2 and down to -2. And we're graphing sines. I'm going to plot my points for the sine. We start here at pi over 12. We go up, come back down, hit the bottom, and back up. Guys, now rather than connect the sine curve, I don't actually want to graph the sine curve. I just need the points. I'm actually graphing cosecant back here. So cosecant, I use that points. If you recall what I just talked about earlier, anywhere the graph crosses the x-axis for sine, we have an asymptote line. So I have an asymptote line here at pi over 12. Going straight down. I have another one here at 7 pi over 12. And I have another one yet at 13 pi over 12. Notice that vertice sticks out kind of like a sore thumb there. That vertice is a parabola that opens up along our asymptote lines. And here's another vertice that opens down along those asymptote lines. So there's our one period of y equals cosecant of 2x minus pi over 6. Now our directions did say to graph one period on each side, so I'm going to keep going this way. My next critical points are 16 pi over 12, 19 pi over 12, 22 pi over 12, and 25 pi over 12. So as I go to put those on my curve, my graph down here, my x-axis, 16 pi over 12 simplifies to be 4 pi over 3. 19 pi over 12 does not simplify. 22 pi over 12 is 11 pi over 6, and 25 pi over 12 also does not simplify. Notice we have our points plotted for sine already, so we just continue the same pattern. We're going up, down, and back up. If I follow my guidelines, asymptote line at 19 pi over 12 and at 25 pi over 12, parabola opens up here. Oops, let's try that again so we don't hit the, try it one more time, don't hit the asymptote lines. I'm 0 for 3, probably because my asymptote line is a little bit too close, but we get the general idea. and here my parabola opens down. And we want a period on the other side, so if I subtract 3 from my numerator, I have negative 2 pi over 12, negative 5 pi over 12, negative 8 pi over 12, and negative 11 pi over 12. So putting those on my coordinate plane, negative 2 pi over 12 is negative pi over 6. Negative 5 pi over 12 isn't going to change. Negative 8 pi over 12 is negative 2 pi over 3. And negative 11 pi over 12 also is not going to change. I can just continue on with my sine curve, so we're going down, back up, here, and here. Asymptote lines that are crossing of the x-axis. Both at negative 11 pi over 12 and negative 5 pi over 12. This parabola is a maximum, so it opens up. This one's a minimum, so it opens down. So we've graphed one period on each side. So there's our first look at graphing cosecant from scratch, amplitude change, a shifting right or left, and our asymptote lines there. Oh, let's go ahead and start over again here then. We have graph two periods of y equals negative 2 plus 1/2 times the secant of 2x plus pi over 3. Oh, this is our vertical translation. We'll just ignore that for now and plot our graph, but it does bring up a great point to make. I'll make it now and also make it when we graph this. But we always make our asymptote lines before we apply this vertical translation. Notice that negative 2 is completely away from our function as far as a product is concerned. So we make our asymptote lines before we make a vertical translation. Once we have our asymptote lines, then we can go ahead and shift our vertices up or down based on the negative 2 and move from there. So here my argument is 2x plus pi over 3. To find a starting point, we'll set equal to 0. To find a midpoint, we'll set equal to pi, or a quarter point, we'll set equal to pi over 2. And to find a midpoint, we'll set it equal to pi. I'm going to zip a little bit quicker through this. Negative pi over 3, divided by 2, multiplying by 1/2, x equals negative pi over 6 is our starting point. Oh, subtract the pi over 3. I'll run through the fractions here again. Have to have a common denominator, so I have 3 pi over 6 minus 2 pi over 6, or 2x equals 1 pi over 6. Divide by 2, multiply by 1/2. X equals pi over 12 is our quarter point. And we'll subtract pi over 3. 2x equals 2 pi over 3. Divide by 2, multiply by 1/2. The 2's will cross cancel, and we have pi over 3 for our midpoint. So as we've done previously, I have 3 fractions. In this case, I have 3 different denominators. 6, 12, and 3 have a common denominator of 12. So I have negative 2 pi over 12. The pi over 12 can stay, and the pi over 3 will change to be 4 pi over 12. Now we can see we're adding 3 to each of our numerators, so we're going to graph or just add to get our next several points. And since I want 2 periods up here, I'm going to go ahead and list all 9 points right off the bat. Simply by adding 3 to my numerator. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 critical points, which is what I need for my 2 periods worth. So we'll go ahead and graph now. Sketching a graph. Putting our x and y axis out here. Negative pi over 6 is this first term simplified. So then I have pi over 12. 4 pi over 12, which is pi over 3, 7 pi over 12, 10 pi over 12 reduced to 5 pi over 6, 13 pi over 12, 16 pi over 3 will reduce to 4 pi over 3, 19 pi over 12, and 22 pi over 12 will reduce to 11 pi over 6. If you noticed earlier, our amplitude here is 1/2. So again, I'm ignoring the 2 for right now. So I'm going to go up 1/2 and down to a negative 1/2. And just to make life simple, and we'll come back to that in a little bit, but I'll go ahead and plot my points for cosine. So cosine as a starting point starts up high. At our quarter point it comes down to the x-axis. Midpoint's down low, and we'll just follow our pattern here to plot the points. Now if you want to go ahead and connect those points for your cosine curve, that's fine, but again remember we are graphing the secant curve. So I'm going to leave those points as they are, and everywhere I have a crossing of the x-axis, I'm going to put in my asymptote lines. So I talked about this earlier, but I'll talk about it again. We make our asymptote lines from the cosine curve before we do any shifting based on a vertical translation. So you can see I have points plotted across the x-axis at pi over 12, 7 pi over 12, 13 pi over 12, and 19 pi over 12. Now, before I actually make the parabolas, I will do our vertical translation here of -2. So each critical point, or in this case, each vertice that I have is going to be shifted down 2 units. So instead of being at a half, I'm going to make this hopefully a little bit simpler. I'm going down, there's 1. Go down to -1.5. There's my second point. And just for visual effect, I'll put -2.5 on here as well. But I'll plot those points. So making it -1/2 or +1/2 will be at -1.5. I don't need to replot the point on the asymptote line because they're already there. So instead of being at -0.5, I'll be at -2.5. And we'll just go through and plot each of these points that have been shifted down. And you can see these are my, I'll go with these two first. These are my low points. So they open down to our asymptote lines. And this point is my high point, so it'll open up. This is a high point on one side, and this is a high point on another side. Okay, so again, asymptote lines were drawn in before the shifting, the vertical translation, shifting up or down, but our vertices for our maximum minimum points for our parabolas were shifted in order to make that graph. So our entire graph has been shifted down by 2 units. I believe that will be it, but let's check and make sure we don't have another one here. We don't, so that concludes our look at secant and cosecant.